In this chapter, we are going to talk about alkynes, and it really parallels what we did with alkenes, which is really helpful because we can see the differences and similarities with those reactions. When we talk about alkynes aren't found in nature very frequently, but one place they are found is in the skin of a poison dart frog. This is an example of a molecule that is the poison, and we can see here where there are alkynes that are found there. Now, let's review alkyne structure. We talked about this a little bit, but I just want to refresh. Alkynes contain a carbon-carbon triple bond, and these are going to have the general molecular formula CnH2n-2. These have 4 fewer hydrogens than the maximum possible for the number of carbons present. The triple bond introduces 2 degrees of unsaturation. Right? Now, we have 2 classifications of alkynes. We can have a terminal alkyne, which is here at the end, and then we can have an internal alkyne, which is in the middle of the molecule. The terminal alkyne is particularly special, and we're going to talk a lot about that reactivity towards the end of this chapter, because you end up with a hydrogen bonded directly to the carbon of a triple bond, and so that gives it some unique properties. When we talk about a triple bond, I want to remind you it consists of 1 sigma bond and 2 pi bonds here, and each carbon in a triple bond is sp hybridized, and it's got a linear geometry with 180-degree bond angles. So, how do we name alkynes? Well, alkynes are named in the same general way that alkenes are named. In the IUPAC system, we are going to change the ANE ending of the parent hydrocarbon to a YNE ending, and then we are going to still choose the longest continuous chain that contains both atoms of the triple bond. And number the chain to give the triple bond the lower number. Now, I want us to look at a few examples. So let's look at this fellow here. Now, one of the first things I want to point out is there's a carbon here and a carbon here, and then there's just triple bond and a carbon here. And this looks weird, but they're trying to show the linear structure here. So we assume a carbon here, and there we go. All right, so we need to find the longest carbon chain. So when I come through here and look at the longest carbon chain, I'm going to choose. This is my longest carbon chain, and I'm going to count my carbons. 1, 2, 3, 4, 5, 6, 7. And so that is going to give me the prefix hept. And then it's a triple bond, so we need to count. And I am going to count from the side closest to the triple bond. So that would be 1, 2, 3, 4, 5, because that's my last substituent. You could keep counting 6 and 7, but that's where my last substituent is. So the triple bond there starts with the 3, so that's 3, and there's the ending -ene. And now I'm going to look at my substituents, and I have 2 methyl substituents, and they're in the 2 and the 5 position. So this would be 2,5-dimethyl there's a dash there, Ch11. Okay, so the chain's numbered to give the triple bond the lowest number. Okay, now a few other things to be aware of. One is the most common, or the smallest, let's say, not necessarily the most common, but the smallest triple bond molecule that you can see here is ethine, which is also known by its common name, which is acetylene. So if you've messed with acetylene torches, that's what you're messing with. And if this group is off of like a substituent, so for example, like off of a ring. So let's look at a ring example. This group here is called ethinyl. Right? Sorry, I'm just double checking that my spelling's correct. So this group here is called ethinyl because what we've done is we said, hey, look, we've got ethyne here, and we're going to drop the ending and add a YL to make it a substituent. And so we drop the E here and do the YL. So we use the cyclohexane as the parent hydrocarbon name, and we number in such a way where that ethinyl, right, ends up with the lowest number because when we look at alphabetical order, isopropyl doesn't come alphabetically first. So when we go to name this, we would use the cyclohexane as the base name. That's cyclohexane. And then what we would do is we would say, all right, we have one ethinyl dash 2 isopropyl cyclohexane. So I wanted to point that out. Then the other thing I want to point out is if you have compounds with triple bonds and there's more than one, then we use diene. So let me move over here. Right? And then if there are 3 triple bonds, that would be triene, like that. And so let's do an example where we have that. All right. So we've got 1, 2, 3, 4, 5, 6 carbons here. And it's a straight chain. And so our prefix there would be the hexa, because there are 6. And then we need to count, and we want these to have the lowest number. So we count from the right, 1, 2, 3. And so this would be hexa dash 1, 3, diene, like that. This is where my southern accent becomes a real struggle between enes and ines. And so that's why spelling is incredibly helpful here. So if you're ever curious about which one I'm saying in the screencast or in class, I am also going to try to spell it for you as well. Okay. Then the last kind of thing is what happens if you have a double and a triple bond? Well, if you have a double and a triple bond, right? These are called ines, right? And when we look at this, so for example, let's name this one. Okay. The chain is numbered to give the first site of unsaturation to the lower number. So when I say unsaturation, I either mean a double bond or triple bond. It doesn't matter which one, but you want to give that unsaturation, that first site, whether it's a double bond or triple bond, the lowest number. So if we start counting over here, we get 1, 2, but if we count over here, we get 1. And so that's the way we're going to count. So it's 1, 2, 3, 4. And so when we name this 5, because we've got a methyl group there, we would say there's 6 carbons, so that's hex. And then 4 is where there's the double bond. So we'd say 4 and En for the double bond, and then 1, and then Yne for the triple bond. Then we go 5 methyl. So that's 5 methyl hex 4-ene 1-ine is the name of that molecule. Now, how do we synthesize alkynes? Well, we've worked on this a little bit before, so this next part is just really a review. But alkynes are prepared by elimination reactions. A strong base, which we talked about before, removes an equivalent of 2 equivalents of HX here, so as HCl, to give an alkyne. And you can either use a geminal dichloride where the 2 halogens are on the same carbon, or a vicinal dibromide or dichloride, a vicinal, geminal or vicinal, where the 2 halogens are on carbons next to each other. And it's just 2 successive elimination reactions to get a triple bond. So we can prepare alkynes that way. Now, we can also prepare alkynes from alkenes. So, for example, since the vicinal dihalides are readily made from alkenes, you can start with an alkene here and convert an alkene to a vicinal dibromide, and then it can go through an elimination reaction to form an alkyne here. So this is just a quick review. We've already done this, and so it's always nice to kind of revisit and just kind of dust off those brain cells of things that we've seen before. In the next screencast, we are going to look at reactions that alkenes can go through. If you have any questions, please feel free to stop by my office.